Okay, thank you. Hope you all had a little break. And it's quite an excellent talk that John has given. It's hard to follow him, but I will do my best. Okay, so today I'll try to tell you how to hide the secrets in software. And my name is Rachel. The fundamental question we are asking here is, what is the minimum information that a computer program that we work with every day really needs to give away in order to do its job? And when I say computer program, you will immediately think about some program written in your favorite computer language, maybe Python, maybe Java, maybe MATLAB. But we know that theoretically, all of those can be translated into this mathematical model called arithmetic circuits in some finite field, ZP. And which basically involves a sequence of addition and multiplication. In other words, every output element is the outcome of evaluating some polynomial on the input variables. Of course, these polynomials are hugely complex, and they might have very, very high degree, for example. The concept of program obfuscation in cryptography, its conception really dates all the way back to the beginning of public key cryptography. And here we're going one step further and ask, can we efficiently actually transform some program that may give away a lot of information into another one that computes the same function, but now give away minimal information? It is really this compilation that we're looking after, and we call it a obfuscator. And of course, we're computer scientists. We want the obfuscator to be efficient, and we wanted to produce an obfuscated program that is not too much slower than the original one, as efficient as the original one. Program obfuscation had been a long outstanding goal, mainly for the purpose of preventing reverse engineering. And there are lots of ad hoc obfuscators out there. And in fact, we humans also enjoy the process of crafting pieces of software that are hard to understand. And there are actually international contests for this. And here, for example, is a winning entry, a C code, which looks rather obscure. And can you guess what it does? Actually, when you run it, it will start to display some animated letters on the screen. Okay. Unfortunately, all these ad hoc obfuscators, one way or the other, tends to be broken by ad hoc deobfuscators. And in order to get out of this repair and attack cycle, that the cryptography community wants to build a obfuscator that we can prove it's secure based on really well-studied hardness assumptions, which are basically conjectures that certain computational problems, such as factoring the products of large primes, are hard to solve efficiently. So before we can start to really think about security in a mathematical manner, we need to first understand what is that minimal information we're talking about that we are aiming for, right? Ideally and intuitively, we really would like the obfuscated program to act like a virtual black box, in the sense that the only information that it gives away are the correct outputs for chosen inputs. That would really be minimum, because we do want the obfuscated program to compute the same function, meaning given it, anyone can choose some inputs they like and evaluate and get the right output. And that would also guarantee that all the secrets in the program that are not efficiently learnable by looking at the input-output behavior of the program would now be really hidden. And this is really powerful. Okay? One is that program obfuscation has been long sought after in software industry for protecting proprietary software. So consider a company who is concerned about giving away its private machine learning program to a cloud, can now first obfuscate it and send the obfuscated version. Now with it, the cloud can provide prediction service to clients on behalf of the company and learn nothing beyond the input-output behavior. We can also use program obfuscation to hide data, not just software, by writing the data inside some obfuscated program. Right, the most naive way is to just hard code a piece of data as a constant in a program that will only output the data when the right secret key is given as the input. And therefore, for adversaries who do not know what the secret key is, virtual black box guarantees that the data is really hidden. And this effectively implements encryption. Of course, now we get talking that with program obfuscation, we can do new and exciting things way beyond the scope of basic encryption. For example, we can enforce really fine-grained control, partial access to the data. So now let's think that here we have an investor who would like to delegate the job of exchange in the stock market to a broker, but is concerned about giving away their complete financial data. What they can do now is to obfuscate, hide the data inside an obfuscated program that will guard the data and only answer certain very specific queries when the matching credential is present. With the obfuscated program, the broker can now make limited query on the data that is sufficient for him to make decisions on the stock exchange, but do not see the data in its entirety. As we can imagine, that program obfuscation can in general enforce any policy about who can compute what kind of function on the data. When combined with encryption, it can also be used to achieve really advanced cryptographic tools. For example, we can enable a processor to compute all encrypted inputs. Here we can give it an obfuscated program that has the right secret key hard-coded inside. The program, when given as input and encryption, will internally decrypt, do the right processing, and finally re-encrypt the processed data. This way that we have effectively implemented one of the magical concepts called fully homomorphic encryption in crypto. But now again, program obfuscation is very flexible. I can also give away part of the processed data in the clear without re-encryption. And now this implements yet another powerful tool called functional encryption. And we can even think about combining both of them together. So with all these great applications in our mind, it comes with great disappointment that it turns out virtual black box is impossible to achieve in general. And this ultimately is because having access to a program that computes the function, no matter how unintelligible it is more information than input-output behavior. Because for many programs, it's actually hard to learn the program from just the input-output behavior. So therefore, BBB is a great goal, except that it's too good to be true. And therefore, we look at a much more realistic and humble goal called indistinguishability obfuscation, or IO for short. And it only guarantees the following security property: that if we started with two programs that really compute the same function, for example, these two ways of evaluating the same polynomial, then we want their obfuscation to become hard to tell apart. In other words, IO only hide the differences in different implementation of the same function. This is indeed much weaker, and now IO is possible. Although on the flip side, it is no longer clear that whether it is really powerful and useful. Somewhat surprisingly that in all the virtual black box applications, the crypto community has managed to replace BBB with IO, including this application for building fully homomorphic encryption and functional encryption. And furthermore, that in the last decade, IO has really changed the cryptography landscape. So here is the cryptography landscape before IO with all these magical primitives and objects that we love. And they are built upon different kinds of hard problems. And they leverage distinct features of each of those hard problems. So for example, fully homomorphic encryption so far, we only know how to build them from lattices. On the other hand, identity-based encryption, we can build from a variety of hard problems, including factoring, lattices, and computational Diffie-Hellman. If we have IO, then suddenly we can build almost all known crypto goals without any other hard problem anymore. In other words, IO can be viewed as really a universal tool for building cryptography. Furthermore, in the last few years, it has really taken us to a brave new world where things that we didn't know how to achieve before or didn't even try to achieve before has now become true. So can we build I/O then? Ever since the first candidate that was proposed about 10 years ago in 2013, a great celebrated work, the community has really poured into huge efforts towards building I/O, and dozens of constructions have been proposed using very different approaches. Unfortunately, up until recently, all these proposals rely one way or the other on some kind of heuristic in the form of newly conjectured hardness. Fortunately, that all this amazing body of work has really laid the ground and forged the path for building I/O. And in two recent works that we managed to finally obtain I/O from well-studied assumptions. And more formally, that we build I/O based on three hard problems. I will read them to you. The first is the learning parity with noise problem over large fields, LPN. The second is the existence of a tool called the Pseudorandom Generator that has a local structure. And the third, we assume that certain computational problems are hard on an algebraic object called the bilinear maps. With these three hard problems, we can construct I/O. And for many of you, maybe none of these problems you have heard of or make any sense, but don't worry that I will introduce some of them later when they're needed. But I just want to note for now that all these problems has had a history of study and application in cryptography, and they each has been studied in various different areas with their roots in information theory, complexity theory, number theory, and algebra. So let me give you just some taste, some high-level idea about how we can obfuscate programs. Really, what we want is to have a way to encode the description of a program, perhaps like an encryption. However, we still want to be able to evaluate arbitrary input X of our choice on the program and obtain the output. Towards this, we quickly realized that in order to hide the program pi, it is not enough to just hide its description. In fact, I must hide all the intermediate computation steps because any intermediate value may help us to reverse engineer information about the program pi. And this computation, the challenge is really that we're dealing with arbitrary program, and hence the computation of evaluating an input may be very, very complex and have a huge degree. And we must hide such a complex computation. Now, this is rather daunting to tackle with right away. And the key idea is that we're trying to transform this very complex computation into another one so that only a very simple intermediate step of just degree 2 needs to be hidden. And the rest of the computation can just be done in the public securely. If we can really minimize the degree of the secret computation to be such a simple degree 2 polynomial, then we know how to hide it because we have this tool called a bilinear map, which essentially allows us to compute degree 2 polynomials on secret values. And bilinear maps can be implemented using elliptic curves, which is a really well-known mathematical tool that we use day to day in order to secure internet today. For most of you, a curious mind, you probably are wondering, what about the degree 3? I mean, what's special about degree 2? What about degree 3? Interestingly, until now, we still don't know a direct algebraic way that can allow us to securely compute degree 3 polynomials. And degree 2 is what we know. Okay, so how can we now transform a very complex computation into one where only some very simple intermediate step needs to be hidden? Towards this, our first action is actually going to transform this evaluation for the input X into 2 steps that we call hide and decode. In those two steps, only the first step, hide, actually depends on the input X to be evaluated. And it will produce an intermediate outcome O, and from which we can apply a decoding procedure in the public to obtain the output. Okay. So for security really hold, let's get thinking, is that I really want this intermediate outcome O to contain only information about the outcome Y and nothing else about the program pi. Right? If that's the case, then indeed the decoding can be done in the public because all the intermediate value also would only depend on the output Y. And so we can think about the hide procedure as some kind of special encryption that really only allows revealing the output for a single specific single specific input and hide all other information about the program. It turns out that this can actually be done using quite classical cryptography tools such as Gabel circuit and randomized polynomials. And this is a great step. And now, if we look closely into the hide procedure, we see that really the most crucial step inside it is evaluating a pseudorandom generator. What is a pseudorandom generator? It's one of the most basic and fascinating tools in cryptography, which allows us to expand a very short, truly random bit string, which we call a seed, into a much longer output that looks random. Okay? We really want the output to be much longer than the input. For example, the input is square root of the length of the output. And here, by random looking, what we mean is that the output R, which we know is not truly random, it doesn't have enough entropy. However, it is computationally hard to tell it apart from a truly random string of the same length, and hence called pseudorandom. So in cryptography, we can build pseudorandom generators from all sorts of hard problems. But we have also wondered for a long time that how simple can such pseudorandom generators be? In other words, what kind of simple functions can already produce random looking outputs? And here, for the purpose of program obfuscation, we don't want just ordinary simple. We want extremely simple. We want a PRG that is computable by just degree 2 polynomials. Can we have it? With extensive effort, unfortunately, up to now, all the proposals have been attacked, and we don't know whether we can have degree 2 pseudorandom generators. So the simplest PRG that we do have this local structure, which means that every output bit depends on just a constant number of input bits. However, that number must be at least 5. And this structure immediately implies that such PRGs can be computed using low degree polynomials. However, again, the degree is at least 5. So we're kind of stuck, right? I don't actually know how to securely compute a degree 5 polynomial. The only thing I have is a bilinear map that can only compute degree 2. On the other hand, that we don't have degree 2 pseudorandom generators. So the final piece of idea is that perhaps we can just walk in between and have what we call, quote unquote, degree 2.5 PRGs. Well, this doesn't really make any sense. So let me explain. Here, we're gonna split the input to the PRG, the seed, into a public and the secret part. The public part called the public seed P, and the secret part called the secret seed S. Again, I want the total length of the public and secret seed to be much shorter than the length of the output, so I gain something. So with this kind of structure, and what do I mean? What do I really mean by the public seed being public? I mean that the output R should still be hard to distinguish from truly random, even when the adversaries are given the public seed. That's what it means that it is public. Now with the two-part input, we can think about the slightly more complex PRGs, which really has degree 2 in the secret seed, and hence it can always be written as a sum of quadratic monomials in the secret seed. But now the coefficients of those quadratic monomials can depend on the public seed And this dependency can be more complex of some constant degree that is at least 5. This is what we mean by degree 2.5 PRG, that it sort of is sitting in between degree 2 PRG and degree 3 PRG. And not too hard to imagine that this kind of structure we can still securely compute using bilinear map, because after all, the computation that depends on secret information, the secret seed here is really degree 2. The final piece of the puzzle is whether I can have those kinds of degree 2.5 PRG. And this is answered affirmatively in the 2 recent works, where we showed that there's actually a way to generically transform a local PRG, which we do have, into a degree 2.5 PRG, using this last assumption, which is the learning parity with noise in finite field. Okay. And in summary, that the approach that we take towards building program obfuscation is really to gradually transform a highly complex computation step by step into one where the part of the computation that needs to be done hidden have lower and lower degree until all the way down to degree 2. Note that in all those transformations, I did not really reduce the complexity of the computation, or the computation is still as complex as the original program, which is necessary. The only thing that has become smaller and smaller degree is which part I need to actually hide. And I want to just mention that in this whole journey towards building I/O, that Simon's Institute have really been a pushing force for the community through multiple programs and workshops. In fact, my personal journey towards building program obfuscation really started here in the Simon's program, in the cryptography program in 2015. And with the program that is running now, that we have the opportunity and the platform to really look forward to what we can further do with program obfuscation. And while we celebrate that we now know that I/O is feasible based on well-studied assumptions, I want to say that we really first just at the beginning of the road towards understanding it. We still need major paradigm shifts, new ideas, so that we can build I/O in an efficient and practical manner. And we still need time to really think and reflect about what program obfuscation can bring us in the future. For example, whenever I say the word secrets, what do you think of? I think about the locked doors, closed safe, classified documents, very, very secure encryption. All these ways that keep secrets secure and safe, but also useless, right? I can no longer compute on these secrets. I can no longer learn useful information from them. However, program obfuscation offers a different way, a way that we can create useful secrets by hiding them inside the obfuscated program, which still allows us to compute on them, but now only those permissible use. And this really depicts, to me, a fascinating future that how we can use secrets and private data in the future. And this concludes my talk. Thank you. Questions? Yes.
Thank you for the great talk. I was just curious what the assumed hardness that's sub-exponential of these problems was.
Yeah, so what it means is that for each of the hard problem, when we talk about computational assumption, we can talk about first, what is the computational problem we're thinking about? And then we can think about what is the strength of hardness we want. And typically the weakest is to assume that the problem is hard to solve by polynomial time adversaries. And the harder problems are problems that are hard to solve for even sub-exponential time adversaries. However, a little bit fine print, the sub-exponential hardness I mean here is not that. What I mean here is that it is hard for polynomial time algorithms to solve those problems with a probability that is bigger than some sub-exponential amount. Does that make sense? Okay, cool. Thank you.
We now